All right, let's get started. So I know on the schedule it says we are going to do 2.4 today and Friday, but 2.4 is not very long. And I really want to take the sweet time getting comfortable with these calculations because 2.4 is going to be a lot more of this. And if we don't have our basics down, there's no point wasting your time. So I really want to go over this with y'all, and then I have some textbooks. So I think for the first half of the class, I want to just do practice problems. And then for the second half, potentially start 2.4. But if we don't start 2.4 till Friday, that's fine too. Because we still have Monday, we have Friday and Monday, and our exams next Wednesday. So if you haven't started your homework yet, please start your homework. Get as much of that homework as done as possible. Because if you wait until last minute to start that homework, it's not going to be beneficial for you for the exam. And our goal is to get you ready for the exam. Okay, let us continue. This was the in-class activity from last class. We didn't really have a lot of time to go through it, but I love this because on our slides, Dr. Patterson had included all of the equivalents for us. We didn't have to really think about what we needed. So now we're going to have to really use this triangle and figure out our equivalents. So number one, so first it says show all work to earn credit and then round to sig figs. So typically if the answer only has 3 sig figs or in the question, your answer should have 3 sig figs. But this one's saying how many moles are in iron sulfite? First, what is iron sulfite? So Fe is 2 plus because of that 2 Roman numeral. What is sulfite? SO3 what? 2 minus, right? So this one doesn't really need a crisscross. This one's just going to be FeSO3. And it's asking, so it's giving us grams and it's asking for moles. So the only conversion we will need is going to be 1 mole equals, and then is the molecular, I'm going to do M mass for molar mass in grams. That's this part of the triangle right here. So M mass of FeSO3. That's the only equivalent we need for this problem. For us to figure out the molecular weight, we would need to use the periodic table of elements to figure that out. So Fe, let me see, I think it's 55.845 plus sulfur. I do not know sulfur on top of my head. 32.059. And there are 3 oxygens. So I got the molecular weight is 135.904. So anytime there is a gram involved in the problem, you have to find the molecular weight of whatever it's asking for or starting with. So that's going to be a first step you have to do is, and that's why we have to get comfortable taking those words and turning it into a compound. All right, now we have everything we need. We have our equivalents, we have our molecular weight, and we can get started. If I have 26.8 grams of FeSO3, I want my one on top and my given on the bottom. So I want moles. And I'm going to divide by my given, so that's my molecular weight. So 26.8 divided by 135.904. And that is, calculator's messed up. $26.8 divided by 135.904. And it should be to 3 sig figs. So 0.197 mole of FeSO3. So that's how you want to, write the whole problem. Don't forget your units because your units would cancel. Did y'all get that?
So I put the 6.02 times 10 to the 23rd.
So the only time you need to think about that equivalent is if they were to ask about representative particles. If they don't mention formula units, molecules, atoms, ions, we do not use the 6.02, that big number. So this one's only asking for moles and it has grams. So we need to be able to pick out which two equivalents are relevant to the problem. And that's going to be the hard part, is picking them out. And it just takes a little bit of practice. For the next one, that's when we're going to need the representative particles. So the number 2 is asking, it's saying how many atoms of helium are in a helium balloon that has a volume of 5.98 liters. Now, representative particles is a broad term for a variety of different things. If I have a balloon of helium, what is the representative particle? So that's going to be formula unit, molecules, ions, elements. It's the smallest unit available. So if I just have helium, what is the representative particle? It's just going to be the element or the atom. So in this case, I'm pointing this out because sometimes you need to do an extra step, and that's when it's asking for something that's not the representative particle. In this case, since only helium is present, if I was to use the 6.02 value, that's going to be the answer. So I can change out representative particles with atoms. So I have 6.02 times 10 to the 23rd. Instead of doing RPs, I'll do atoms of helium equals 1 mole. But in this case, it's asking about liters. So 22.4 liters. So I'm just going to the triangle. And in this case, I'm going between this one and this one. You can convert everything into the mole first, but it's sometimes more efficient if you could kind of skip that step, going from one thing to another. So when I set it up, I want my liters on the bottom, and I want what I'm looking for, my atoms on the top. And when I plug everything in, I get 6.02. I got 1.58 times 10 to the 23rd. Does that one look a little bit better? Like, is that one a little bit more, like, let me know if I need to break it down further or,
I'll do more.
yeah. For the next one, it says how many atoms of oxygen are in 9.7 moles of diphosphorus pentoxide? First, what is diphosphorus pentoxide? P2O5. What is the representative particle for P2O5? Yes. So if I was to use this 6.02 value right here, it would give me molecules of P2O5. But the question is asking for atoms of oxygen. So that's when we need to remember that if it's asking for a smaller step than our representative particles, we have to do an additional equivalent. But let's write out those equivalents because that's always going to be my first step while we're learning this. It's asking for representative particles and moles. So my first equivalent is going to be 1 mole equals 6.02 times 10 to the 23rd. And instead of doing representative particles here, I'm going to do molecules because molecules is the representative particle for this compound. If this was ionic, it'd be formula units. If this was an ion, it'd be ions. But I'm going to do MC for molecule of P2O5. That's going to be my first equivalence. But my second equivalence is if I have one molecule of P2O5, how many atoms of oxygen? 5, because that's the subscript. 5 atoms of oxygen. So now that I have my equivalence, I can set up my problem. I'm starting with 9.7 moles of P2O5. My answer also should be in 2 sig figs. The first thing I need to do is use this first equivalent. So I want mole on the bottom, and I want molecules on top. Okay. That way my moles will cancel, and I'm left with our representative particle. The next step is going to be going from molecules to atoms of oxygen, which we've already done over and over and over again since the dimensional analysis class. So that's the easy part, is going from molecules to atoms. We just have to remember to add that extra step. I have 5 atoms of oxygen for every 1 molecule of P2O5. So now my molecules cancel out, and my answer will be in atoms. 9.7 times 6.02 e to the 23rd times 5. And I should have it 2 sig figs, so it's 2.9 times 10 to the 25th atoms. And you want to make sure you keep those units when you write your overall answer. If it asks for molecules of P2O5, you could stop it there, but it didn't. That's why we had to do that extra step. For the last or fourth one, what volume is occupied by 165.6 grams of propane? So in this case, we have to be able to create an equivalence using volume and grams. So if I go back to my triangle here, I already have one right here. It's given me the volume, 22.4 liters per mole for the gas. But it doesn't give me a number for the molecular weight. So in this case, we have to solve for it. What is propane? Yes. So I need to figure out, okay, each of those carbons is worth 12.01. There's 3 of them. And then there are 8 hydrogens. So if I add all that up, I get 44.01. Yeah, I got 44.094. You really don't want to round, but in this case, I'll round for today. And that's, I got, oh, yeah. Oh, 9, you're right. It would be 0.1, so I'm not rounding. Grams per mole. So my equivalence here would be 22.4 liters of C3H8 equals 44.094 grams. Do you see how I was able to do that? You take the units of the given and the want, and I go up to my mole triangle, and I find it. I have liters here, that's volume, and I have grams here. So the only 2 numbers I need are these 2. I don't want to accidentally think about this one because it didn't mention molecules or formula units or atoms. I want to ignore it because it's not part of the problem. I only want these 2. So I'm going to come down here and I'm going to write out that equivalent to help make my math a little bit better. My units cancel. And this one has 4 sig figs, so I'll do it. 4.13 liters of C3H. Also double check my math, because you could do this times this divided by this, or this times, and then put this in a fraction. Sorry, it keeps focusing. How about that one? Is that one a little bit better? Okay. The last one. How many sulfate ions are present in 97 grams of aluminum sulfate? So this one is I would say this one's a really good problem to really test how well you know this concept. It's asking for first grams of aluminum sulfate. So the first equivalent I will need to think of, if I go back up here, is the molecular weight of aluminum sulfate. So aluminum, does anyone know what is the charge aluminum will always have? What about sulfate? So SO4 2 minus, this one will require a crisscross, and this is Al2SO4 in parentheses, and that would be 3. It's very important for us to get this correct, because if I was to find the molecular weight of this and I didn't, it would greatly affect your overall answer. It's not such a big deal if it was a short answer problem, because you can get partial. But if this was a multiple choice question, you would lose all points, and we do want to avoid that happening. I need the molecular weight of this aluminum sulfate because it says grams here. So I need to go to my periodic table of elements and calculate that. So don't remember that if it's in parentheses and there's a 3, I have to multiply the 3 by everything inside. So that'll be 3 sulfurs and 12 oxygens for me to do all this math. I'm going to go to the periodic table of elements because I don't have this memorized. Big number. And the molecular weight, 342.14 grams. That's my first equivalence. My second one's going to have to incorporate this part. It says how many sulfate ions are present. What type of compound is this? Is it ionic or is it molecular? It's ionic because it's a metal and a non-metal. What are the formula units for this compound? Sorry, I just gave it. What are the representative particles for this compound? And that would be formula units because it's ionic. So if the question is asking for ions and I know that the representative particles are not ions, I have to remember there will be an extra step. So I need to come back up here and say, okay, ions, formula units, all of that falls under this part of that triangle. And then I have this part of the triangle. So my first equivalent is to take my molecular weight, so 342.14 grams of Al2SO4 is equal to the representative particle, 6.02 times 10 to the 23rd, and I'll just do a lowercase fu, I know, it's funny, for Al2SO4. But then it says ions. So my next equivalent, so previously we've been doing atoms, but ions is another way of doing this. If I have one molecule or one formula unit of aluminum sulfate, how many sulfate ions are present? I'm looking at the subscript. There are 3 sulfate ions per every 1 formula unit of Al2SO4, 3, or sorry, yeah, Al, all that. So I'm going to do 1 Fu of Al2SO4 3 is equal to 3 ions of SO4 2 minus. So you want to have those equivalents ready. If you can do this in your head, that's what's wonderful. But until you're comfortable with that, I'd write it down. Go to the triangle, because usually the triangle is provided for you. And then you want to pick the ones that we're focusing on. So we have this one and this one, this one and this one, and we might have to break it down a little further, and that's okay. So first, find formula units, and then you can find ions. Also, the is going to be the 2 sig figs as our overall answer. And when you put it all together, it'll look something like that. And I want to make sure my units cancel. So my grams will cancel out and my formula units will cancel out. If they don't cancel, you probably flip these and have these in the wrong location. Remember what you want on top, what's given on the bottom. So grams need to be on the bottom here for this to cancel out. Formula units need to be bottom here for that to cancel out. And when I plug those in my calculator, 97 times 6.02 divided by 3.4 times 3. So 2 sig figs, 5.1 times 10 to the 23rd ions SO4 2 minus. This is a good challenge. While you're studying for the exam, hopefully once you've finished all of the homeworks and you're comfortable with the homeworks enough, you've done the quizzes, a great way to continue practicing are using the exam questions themselves or coming back to these worksheets, printing out a blank copy and trying to go through these worksheets again without your notes. If you can do this without your notes, then you're going to be ready for that exam. But it's okay at first if you need to have some notes in front of you. The key is available for you. So if you want to check your answers to the key, you always have that. Just don't be reliant on the key to answer it. You want to be able to look at the question and get started without assistance. And then you can come back and look after it. But the more you do this, the better you'll get not using your notes. Okay? Okay. Let's move on to, I have the textbook here. I went and I just found some questions. They're going to be a little bit easier, but I want to kind of go back to basics for a bit. And then for maybe like the next 20 minutes, we'll probably just work on this until the break and then we'll move on. Yeah. I want you to do 43 and 45. So do 43 A through C and then do 45 A through C. We'll do that for a few minutes and then we'll come by and do together. And if you want to keep going, you're welcome to either move to over here or just do 47 and 48. I wrote down some of these questions on a piece of paper for us to go through. Zoom out a little bit. So, sorry about my handwriting. These are great questions because it asks for two ways, convert to moles and to atoms. Sometimes you can go straight through and go to atoms, and we'll do all of that. So just remember those conversions. If you see grams, you're going to need the molecular weight. I forgot to bring a periodic table of elements with me, so I'm going to keep going back and forth. Well, I have my app on me, so I'll get my app up. First, I see grams. Sorry. Let me get my periodic table of elements app in front of me. So if I say grams of sodium, I'm going to need the molecular weight of sodium. In this case, that is 22.99. So for me to go from grams to moles of sodium, I need the molecular weight. So Na, I'm doing M mass for that of Na equals 22.990 grams per mole. So 23.4 grams of sodium metal. And if I want moles on top, I will invert this because I want moles. (23.4) divided by 22.99, and that gives me 101. And 3 sig figs here, I want my answer to have 3 sig figs, so it's 1.02 because that next digit is bigger than a 5. So that's converting from grams to moles. If it asks from moles to, or from grams to atoms, then we need the equivalent of the representative particles. Since this is one element, then my 22.990 grams of Na will equal 6.02 times 10 to the 23rd atoms of Na. That's just going back to that table. Sorry, the triangle I'm thinking of. So 23.4 grams of Na times 6.02 times 10 to the 23rd atoms of Na divided by 22.990 grams of Na. And those grams will cancel. And I got 6.13 times 10 to the 23rd atoms of Na. These are great practice. So essentially you're doing the same thing over and over. Pretty much you're replacing this front number with whatever number is here. And then you're replacing this bottom number with whatever the molecular weight of the other ones are. So the molecular weight of phosphorus, I don't know, 30.974 grams per mole. So to go to moles, I just need to know 1 mole equals 30.974 grams of P. For the next one, I need to know that 30.974 equals that number. So I'll start with the first one, 18.2 grams of phosphorus. I want my 1 mole on top, my 30.974 grams on the bottom, and that gives me moles of phosphorus. And there's 3, so 5, 8, 8. For the next one, I have to know that 30.974 grams of phosphorus is equivalent to the atoms. Since it's only one element, my representative particle will be atoms. So 18.2 grams of phosphorus times 6.02 times 10 to the 23rd atoms of phosphorus divided by 30.974 grams. Cancel. .54 times 10 to the 23rd. Is that any better? Or how do you feel about just doing moles and atoms?
Pretty good, I think. Kind of plugging it in slightly different, but I'm getting.
That's fine, as long as you're getting the right.
Down to the-
Mhm.
And I just multiply that by the 6.02.
Yes. Yeah, and you can also skip this next step by just taking whatever you get from moles and multiplying that. So you would be right doing that method too. Yeah, so you're not wrong. So if I did this one, doing that method, carbon's molecular weight, so 1 mole equals 12.01 grams of carbon, which is also equal to 6.02 times 10 to the 23rd atoms. So if I did one long equivalent conversion, so 192.3 grams of carbon times 1 mole of carbon divided by 12.01 grams of carbon. That's another way you could do that. So the moles cancel, the grams cancel, and you'll be left with atoms. So whatever you prefer, that's a-okay. As long as you're, this is the way that Dr. Patterson wants you to kind of be more efficient and skip steps. But for me, I'm very comfortable with my math, and so I like to do it all like this. But we're trying to help students who might make that math error kind of help and be more efficient. And I'm not going to tell you either way you're wrong. Do what is best for you.
I think I'm being less efficient, but I'm making sure I'm not skipping.
Yes.
Like
Yeah.
I do equations for it.
Yeah, I feel the same way. Like I'm okay with myself being less efficient just because I know I can do it in a timely manner. And I'm okay with that. So I just want to show y'all many ways that you can do this. You can get the right answer, and that's fine. And I got that number, 9.64. For 45, convert each of the following moles and this is supposed to be molecules. All right, so let's do the same thing here. But first, if I give us anything in grams, we need the molecular weight. So I'll tell you now, the molecular weight of water is 18.02. And the representative particles, if I was to use the 6.02 in this case, would be molecules. So I don't have to do any extra steps here. If it said atoms of oxygen, I would have to do an extra step, but this one's just asking for molecules. So I can type, I can write it out like this, 23rd molecules of H2O. I can kind of create this giant equivalent here to help make my life a little more simple. So 11.3 grams of H2O. If I wanted to do the first step and go to moles, I would use this equivalent. And if I wanted to go straight to molecules, I would use this equivalent. So I'll do it all at once. So grams times 1 mole. And if you were to leave it at that, that would give you moles. But if I wanted to add that extra step to find molecules, then you do these equivalent. They will both get you the right answer if you were to go straight to molecules, which which is what I'll probably do for the rest to save time. So this version is just getting rid of this additional math that you're not actually typing into your calculator. It is relevant for units, but it's not going to be relevant for your math. And that's why Dr. Patterson encourages you to be a little bit more efficient there until you're really comfortable. But if this makes more sense to you, go for it. So those grams will cancel, the moles will cancel, and you'll get molecules. In this case, same thing. Grams will cancel, and you'll be left with molecules. And I got 3.77 times 10 to the 23rd.
We don't also need to find the moles.
You do, yeah. I was just skipping a step because I'm being lazy, but you're absolutely right. All right. I'm going to skip to the next problem. Let's go through it together because the next ones were a little bit and challenging. This one said how many atoms are present, sorry about my handwriting, in 140.2 grams of zinc metal. So this one, we also need that triangle. It's saying grams. So if they give me grams, I have to instantly think molar mass. If it asks for atoms, I could potentially think represented particles. So if I just have one element, and that's zinc metal, then my representative particle is 6.02, or it is atoms. So I can write out my equivalents here. 1 mole equals 6.02 times 10 to the 23rd atoms of zinc. But I can also keep going. The molecular weight of zinc is 65.38. So for me to go from grams to atoms, I just need these two. I can leave out that middleman. So if you would rather convert everything into a mole first, you can convert grams to moles with this conversion. That's one step. And then you can do moles to atoms with the second step, or you can just skip that mole and go straight to it using this method. Double check your units cancel, because if you were to flip this, you would get a very small number, and that wouldn't make sense because you should have a lot of atoms in these samples. So too small is just, double check and make sure your math's correct. But does that seem a little bit easier? No? No? Or yes? Okay. All right, let's start from the beginning. If I had 60 grams of zinc, how many atoms? Go ahead and do that math. What'd you have?
5.
Yes, I got that too. So I wrote down two ways you can do it. If you prefer option one, where you go from grams to moles and then moles to atoms, that's one way you could do it using this equivalent that we made. If you want to use what I did right here, I went from grams of zinc straight to atoms by taking out that middleman. But this is just going to take repetition. So if I was to give you 30 grams of zinc, 80 grams of zinc, 100. So as you're practicing this, you can always change up your numbers and see if you get more comfortable with it if you play around with that. So I would do that until you get more comfortable with the process, or if you want to just keep the number, but change out the element. Let's do phosphorus. Let's do chromium. So these are ways that I can ask the same question over and over again, but I'm changing the number here and I'm changing the element. Or I'm changing atoms to molecules if I was to ask about H2O. So the questions are not going to change. I'll tell you that. It's not going to change. I'm not reinventing the wheel, but I have so much I can play around with that could be a good challenge. And it just takes practice. So we have one more minute. Let's do one more. And then we'll start the mental break. How many molecules of HCl are present in 2 moles of HCl? First, HCl. What type of bonding is happening? Covalent, molecular, or ionic? So H is not a metal. I know it's on the first column, but don't assume it's a metal. Yeah, this is a molecular compound. So when it says how many molecules there are, it's just asking me what is the representative particle. So I need to go back to that triangle and say, okay, 1 mole of HCl equals 6.02 times 10 to the 23rd molecules of HCl. So ignore that. I'll stop it in a little bit. So representative particles to moles. This is what this problem is just asking, going between these two. So the only things I care about are this equivalent. So if I have 2 moles of HCl, I want my 1 on top and my given on the bottom with these equivalents. So these are the equivalents we put here. I got 1.2, it's only 2 sig figs, so 1.2 times 10 to the 24th molecules of HCl. But if you have your ebook and you would like some additional practice, first finish your homework because that at least you're getting a grade for. But in the back of the book, or sorry, in the end of the chapter, this is chapter 7. Oh, I took it out. But like even going through the chapters itself, what we were doing yesterday or Monday and today is just 7.1 and 7.2. It's like finding the molecular weight. Okay, once you're comfortable with that, finding those mass percents. Are you comfortable with that? 7.2 is when we start doing these conversions. And then if you need some review, and maybe I'm not doing the best job, they walk you through how to do all these conversions. And then they have additional problems. So it says try it. So can you try? This is 7.3. We're not, 7.3 is fine, but when you get balanced, that's when we're doing something a little different. So we're just doing 7.2, and then you want to try practicing it. Can you go from grams to liters? Can you go from moles to liters? Can you go from atoms? So things like it just is going to take practice. And I recommend the back of the book, back of the chapter at least, practicing all these problems. So like I highlighted everything that would be a good challenge as you're going through it. And these are also good and challenging too. but the more you do it, the easier it will. All right, any questions on that? All right, 12:52, let's come back at 12:57 and continue on with 12.4, or unit 2.4, sorry. Okay, let's move on to 2.4. We have today, Friday, and Monday to get ready for the exam. And since units 2.3 and 2.4 are going to be hefty on a little bit of math, I plan on either making new worksheets or just getting a lot of practice with this so you can get more and more comfortable before the exam. But please don't wait until maybe Monday to start practicing. If you have time and, of course, bandwidth now, start getting the practice out of the way now, because when we come into review, you don't want to be relearning anything on review days. You want to be ready to practice it and understand before you come in. So that's going to be a big key factor. If you come in on Monday and we're just straight reviewing and you're pretty much learning it, that's going to be like, oh, okay, we have to go home and do a lot of prep work, and we want to avoid that. So 2.4, it's a very short lecture, but it's a lot of information. So I plan on maybe learning some of it today and then doing a lot more of it on Friday. So I need to do worksheets, get a couple more worksheets. Maybe we'll do some more textbook. But reaction stoichiometry. Stoichiometry is a fun word, and it's going to be so important when you hit Gen Chem and engineering. So we want to get very, very comfortable recognizing stoichiometry. Everything also comes back to the triangle, where stoichiometry is all about equivalence. It tells you ratios, equivalents. We've already kind of hinted at stoichiometry before when we were balancing reactions. So we need to get very comfortable with this mole triangle so we can start utilizing stoichiometry with these ratios. So we're using this triangle to convert the units for a sample. Remember, you don't have, everything will go back to a mole. So if you prefer to get everything into a mole first and then convert it to something else, you are fine. That's the way I do it. And I'm not going to say I do it the best way. I double check my math. I'd rather make sure I'm 100% correct. But if you want to save steps, you're always welcome to, use the triangle. Go from one point to another point to skip the mole, because the mole's always going to be there. All right, stoichiometry is all about ratios. So previously, we worked on balancing. Balancing is going to be so important for this reaction, because if I have everything ones and it's not balanced, your units, your numbers will be very incorrect. So the first thing you want to do with these problems is make sure that these reactions are balanced. Sometimes they're nice and they'll say, okay, you have a balanced chemical reaction. It'll save you some time. But these numbers, these coefficients that are out front, tell you so much about it. And I can relate it back to that triangle. This could all be atoms. This could be, I have one atom of N, or this is not an atom, I'll do molecule. That's not a pure molecule equals 3 molecules of H2 equals 2 molecules of NH3. So it could be molecules, it could be moles, it could be liters. It's all a ratio to each other. For this reaction, this balanced reaction, it requires 1 N2 plus 3 H2. And when you combine those two substances together, it produces 2 NH3. So regardless of what we say in between, it's all about those ratios. Those ratios, that's what stoichiometry is it could be moles. Most of the time we'll say moles. If I have 1 mole of N2 plus 3 moles of H2, it will produce 2 moles of NH3, because I think the mole is probably the easiest concept to think about. But when you have a balanced reaction, there's so many different things it could be. It's all about those ratios. Yeah, so ratios. There is no element or unit behind ratios, but you can replace that with something. All right, there are many different approaches for solving these types of problems. If you take a look, I do have a worksheet that I did publish right before coming into class today. And I have not published the key yet. So if we get to that worksheet, I will publish the key after today. But I do want to show you the key real quick. Here's the key. When you take a look at it later, I always solve it in two ways. There is the approach that Dr. Patterson wants to show you on how to be more efficient, but I will also show you my preferred way, which is the standard American way to solve these, which you might have already learned in your chemistry classes. Neither of these are more correct than the other. It's just what works best for you. Both will give you the right answer. So the standard American way to solve these problems are converting everything into moles and then using those moles to convert to other units. So it's more steps, and it's powerful because it's easily expanded to solve a huge variety of problems. And when you're comfortable with that and you move upper chemistries, it really helps your dimensional analysis practice. It's probably what you've already seen when you were learning in either high school or if you've taken previous chemistry classes. Dr. Patterson is going to teach a new method to help eliminate fewer steps, and it's not going to be what you see. And if you take Gen Chem 1, it's probably not going to be what your professors will teach unless you take it with her. But if you're comfortable with this method, it's a great way to get the right answer quicker. But most importantly, use what works best for you. Okay. This is kind of going off of her method, but it's not incorrect. So the most popular way when we have these balanced reaction is we always make this assumption that of these ratios. 1 mole of N2 is going to be this, I need 1 mole of N2 and 3 moles of H2 to produce 2 moles of NH3. But if I use her triangle, I can replace the mole with anything on that triangle. It could be molecular weights, it could be liters, it could be representative particles. The only thing that I have to make sure I'm consistent with is whatever coefficient is out front needs to follow, because it tells you how much. If I was to compare N2 to H2, there's a very big difference between the amounts in this balanced reaction. So I have to make sure that my coefficient, my number out front, follows when I do this math. But if I'm comfortable recognizing this and I want to go between grams of N2 and liters of NH3, all I have to do is kind of pick out those two, and I can do a quick conversion. I can do a quick equivalent setup using these two. And that's what these problems are going to do, is going from one thing to another thing using the stoichiometry. All right, so we're going to build our own conversion factors as needed for dimensional analysis using any two of those relationships. So don't forget, your coefficient needs to be out front, whatever the balanced reaction, times whatever you pull out of the mole triangle. And I'm going to show you both ways. So if you don't like this way, there's another way to do it. So standard way is given number, unit, and chemical over 1, convert everything into moles. Once you convert to moles, you can then convert it to what you're looking for. Those coefficients are going to be what we use for the mole conversion. The shorter way is you just go straight through it. You just include those conversions out front. So you build. But the best way for me to show you what I'm saying is, instead of me kind of writing it out long on a slide, is show you what I mean. All right, so this is going to be option 1. So let's do standard American. I love the way these questions are worded, because it's going to really require everything we've utilized since the beginning of class, all for one question, which is going to be very helpful to help us study. How many liters of oxygen are needed to burn 50 grams of methane? So first things first, they were not very nice. They didn't give us a reaction. They didn't give us a balanced reaction, but we are capable of creating one. So methane is CH4. And we know that this is going to be a combustion reaction because it needs oxygen. So I'm going to add O2, and it's going to produce CO2 and H2O. Is this balanced? Okay, so all of these are going to require us to balance before we can even get started. So I'll do C, H, and O. So on the left-hand side, I have 1 carbon, right-hand side, I have 1 carbon, left-hand side, I have 4, right-hand side, I have 2, oxygen, 2, and 2. So I need to focus on those hydrogens. So to do that, I'm gonna put a 2 out front to bring this to a 4, but it messes with my oxygen. So now I have 4 oxygen. Oh, I messed it. It was a 3. Sorry, you caught that one. I was wrong. So at least my carbons and hydrogens are balanced, but for me, I'm gonna have to put a 2 out front of the O2 to get that balanced. Now it's completely balanced. So you want to be able to go back to 1.7 and be able to balance this, okay? First step, done. We made sure it was balanced. The second step is we need to figure out how to go from grams of methane all the way to liters of O2. There's going to be several steps in the way. So using the standard way, the way that you do this is you have to convert everything into moles. So you have to use the molecular weight to go from grams of methane to moles of methane, and then to go from moles of methane to moles of O2, you need the stoichiometry, and then moles of O2 to liters of O2. So if I use the standard American way, or I can't say American, it could be any way, standard way where I do multiple steps, it would look something like this. First, the molecular weight of CH4 is, let me find it, because I don't feel like doing it again. 1 carbon plus 4 hydrogen is 16.042 grams per mole. So if I have 50 grams of CH4 times 1 mole of CH4 divided by 16.042 grams of CH4, all I do is take the molecular weight and I reverse it because I'm trying to get moles. And then I use stoichiometry. Find a different color. I need to convert from one thing to the other. And I'm assuming all of it is moles. So for me to convert from moles of CH4 to moles of O2, I want my 2 moles of O2 on top divided by 1 mole of CH4. And lastly, to go from moles to liters, I just need to remember from the mole triangle, 22.4 liters of O2 divided by my units will cancel, and I'll be left with liters. So this is the standard way where you convert everything into moles, and then you use stoichiometry to convert from one thing to the other. And then once you have it in moles of what you're looking for, you can then go into the units you're looking for. I'm going to erase this now and show you the other method. Let me know if you need more time.
Where did the 2 moles of O2 come from?
The coefficient. Yeah, because it's asking for specifically oxygen. If it was asking for one of these, I would pull one of those coefficients. But since it's only asking for O2, I'm pulling that number from there. Okay. So the way that Dr. Patterson likes to teach is instead of doing it in 4 steps, you can actually do it in 1. The first thing I'm going to do is pull down, you're starting with grams of methane. So I'm going to do the molar mass of CH4. And then in parentheses, I'm going to put the coefficient out front. All right. Then it's looking for liters of oxygen. So I'm pulling from my triangle right now. So these numbers are coming from the triangle. So I need to put in parentheses what is coming from the triangle, 22.4 liters of O2. and I put an equal sign between them, because that's the only thing that matters. If it was asking about something else on this balance reaction, we'd do something else. But I'm not gonna waste my time on anything else except what it's giving me and what it wants. So it's giving me grams of CH4, so I know I need the molecular weight of CH4, and it wants liters of O2, so I just need that conversion. So I'm gonna start with what I'm given, 50 grams of CH4. And then I'm gonna use this as a conversion factor. So in the top, I'm gonna put what I want, my liters of O2. In the bottom, I'm gonna put the molecular weight, but don't forget those coefficients. Okay. That way the grams will cancel and I'm left with liters. I'm gonna round up to 40 to keep it as sig figs. Both would give you the right answer. Both. I double checked all my math because I'm like, I'm a stickler for what I've always been taught. But this is also a fun way of saving yourself time and potentially making a math error earlier on. So you just have to create the equivalence based on that triangle. And this is going to require a ton of practice to get more comfortable with. And I have plenty of examples. Does anyone need me to go back? Please don't hesitate to ask, because I know that this is a very difficult concept. And I'm so excited to be breaking it down like this, because when you hit Gen Chem 1 in engineering, we're going to expect our students to already kind of be able to do this. We'll reteach it, of course, so it won't be brand new. But you're going to be expected to go a little bit faster with the concept. So I'm very excited to be able to break it down a little bit further. So I'll tell you now, for our exam, you might not need to do all these steps. You might be given a balanced reaction and you'll have to do the steps based on that. But I love the way these questions are structured, because it's going to be able to take everything we've learned so far and really challenge us. So this one's also quite fun. Iron 3 oxide can be reduced to iron metal by heating it in hydrogen gas. So in this case, they do not give you a balanced reaction. I have Fe3 plus and O2 minus. I have to crisscross, because in order for us to have a balanced reaction, we have to be able to create the equations properly. So it'll be Fe2 O3. That's going to be very important, because iron oxide is not FeO, not. So iron oxide can be reduced to iron metal by heating it in hydrogen gas. So I know my iron oxide is a reactant because I have to heat it in hydrogen gas. So Fe2O3 plus H2. And it says that reduced to iron metal, that tells us that iron by itself is a product. And it says water is a byproduct. So this is my reaction, but is it balanced? It's not. So the first thing I want to do is balance kind of everything else. It's very difficult to balance odd numbers. So you can always put a number out front. Oh, sorry, I'm going off the wrong direction. Actually, this one's not so bad. Skipping the gun. If I put a 3, because it's not O2, if it was O2, it's very hard to get that one balanced, but it's by itself, so it's just 1. If I put a 3 out front of here, I now have 3 oxygen and 6 hydrogen. not so bad. On the left-hand side, I can get the hydrogen balance by putting a 3 out front to get 6. And then lastly, you want to leave your pure elements last. To get that balance, it's now going to be a 2. That's going to be the first thing, is going back to being able to balance these. Once it's balanced, we can now create those equivalents. So I'm going to do the method that Dr. Patterson is teaching. So it says how many formula units of iron oxide so that one's going to be 6.02 times 10 to the 23rd formula units. And in parentheses, I'll put a 1. Just, you want to make it a habit. You don't need the parentheses if there is a 1 out front, but I'm going to make it into a habit. You're welcome to kind of skip that step. So it asks us how many formula units of iron oxide are needed to make 100 grams of iron metal. So the only 2 things I need to create the equivalents is I need iron oxide and iron. I can ignore the other 2. You can put an X on them, whatever you need to just be like, don't play around with that. So it's giving us grams of iron metal, and it's asking for formula units. The good news, iron oxide is ionic. The smallest represented particle is formula unit. So I can leave that one as is. I don't know if I have a lot of space, but I'll try to like squeeze it underneath that. So if I have 100 grams and it's saying of iron metal, so I'm going to focus on Fe by itself. If you were to accidentally flip this, that would mess up everything, but it says iron metal times, in the top, I'm going to put what it's asking for. Actually, I didn't give myself a lot of space, but I want space. So I'm going to rewrite this. I just rewrote it as equivalent. I put an equal sign because we're using them as an equivalent. And if you're wondering where I got the 55.845 from, it's just the molecular weight of iron. I got it from the periodic table of elements. Okay, no worries. The question is asking for formula units of specifically Fe2O3. So that's our goal. That's why it's in the numerator. But then we need to get rid of the denominator, so we need to get rid of the grams, and that's going to be coming from the molecular weight. So if I was to go back to the beginning, once we balance everything, Sorry, did you get the math or is the setup? The math, okay, so the setup was okay?
Yeah.
Okay,
I was just putting it in wrong.
let me double check.
1.68.
No, I can definitely be incorrect. So what I do is like, kind of like do an additional parentheses around this in my calculator and then do a big one. So 100 times. Two times 55.8. Okay, I got the same thing. So what I typed in my calculator looked like this. You can leave the one in there, but I kind of don't like to type it in because I'm lazy. So is that how yours looks when you type it in?
I got another different number.
You guys,
Maybe put the denominator, right?
okay. So does everyone have that when I type it in? This is gonna take some extra parentheses. But if you want to break it down, like you can always like do this first and then multiply it by 100, or just do what you've been doing before where you focus on the top and then divide it by the bottom.
That's what I did the first time. I did 100 times the 6.02, times 10 to the 23rd. Got that answer, and then divided that by 2 times 55.845.
Was that in parentheses? Because it probably divided it by 2, enter, and then multiplied it by, but that 55 also needs to be in the denominator. So make sure you, if you, that's a perfect way to do it, just keep in parentheses. Yeah. All right, I'm gonna have y'all help me with this one. Iron metal can react with fluorine gas. How is that going to look if I write out the equation? So iron metal, is it attached to anything? It's just going to be pure iron. Iron metal looks like this. Chlorine gas, is that going to be just Cl or is it going to be something else? So it's a Brinkelhoff, so Cl2. And then it says produces iron 3 plus and chloride minus. So it says iron 3 chloride. What is that going to look like? Yes, FeCl3. So we have to crisscross it. Is it balanced? It's not balanced. So to do that, what should I do first?
Put 3 in parentheses, like 2 on the left side.
If I did that, that would mean I would have an even number. So no matter what number I put here, it'll be even, but this is always gonna be odd. So that would definitely could work, but we have to first figure out a way to get this even. Does that make sense? Yes, that's where I would start, is I want to get my chlorine even because I have Cl2 on the other side. So if I put a 2 out front here, that means that now I have a chlorine even number. So I'll have 6. And I'll have a 2. So now that it's even, it's easier for us to do. So if I do that, I now need to put a 2 out front of here. And then for this to have equals 6, I'll put a 3 here. But yeah, you had the right answer anyway, putting a 3 out in front of the CL2. Yeah. Okay. All right. So it says, how many moles of iron 3 chloride can be made from 15 liters of chlorine? So chlorine is here. So from the mole triangle, I know that it's 22.4 liters of Cl2. And from the mole triangle, whatever the inside of the mole triangle is just 1 mole. Just make sure you have the coefficients follow. Now you set it up. So what do I put in the top?
The 2 moles of
Which means on the bottom, 22.4 liters of Cl2. And when I plug this into my calculator, I got 0.446 liters. Oh no, moles. So I want to save the rest. I mean, there's a bunch of more examples, so I'll keep doing the other examples next class. But I kind of want to play around here and like, what if I was to ask for grams? Like, what if I was to say, instead of finding moles of FeCl3, how many grams of Fe? What would I do? That would change the equivalence. So instead of us focusing on FeCl3, I would then need to do of Fe. But look how little I actually had to change the problem. The 2 is the same thing between the two, so I didn't have to mess with that. All I had to do is just change my equivalent of what it was looking for. So similar math. What if I, instead of asked for that, I asked for formula units of FeCl2? Yeah, oh, sorry. Like if I asked for that instead, all I would have to do is, put that here. No matter what I ask you, I can give you the same exact problem. All I can do is just, give you different numbers. But you just have to be able to create an equivalent. And then using that equivalent, you just got to plug and chug. It's not so bad the more you do it. And then sometimes they're nice and they'll give you that balanced reaction, but I can ask you this problem a million different ways. So you might see a problem similar to this on the exam, and especially on the worksheet we're probably going to hit next class. The problems themselves, the setups are not going to change. Like I might have this exact same setup, but I might just change this number. These are just such a good way to practice. It's like no matter what I throw at you, how can you approach it? And that's going to be how comfortable you are with it. All right, I'll leave it at that. I would say right now, if you have time, open up your homework, maybe answer one of the homework problems for 2.4 and see how that looks. But if you need to go, it's a 1:37. The class ends in 3 minutes. But I don't mind staying for like an extra 10 if y'all have any homework questions. I definitely want to help if y'all have homework questions.